All right, let us summarize electrostatic energy. UE. Well, first of all, we were able to write down in differential form a combination of Maxwell's equations in order to find a second order equation, which is called Poisson equation. So according to Poisson equation, given a volumetric charge density ρ, which is continuous and limited in space, we can find the scalar Laplacian of the electrostatic potential V is equal to minus ρ divided by epsilon naught. And again, the conditions are that ρ has to be continuous in capital omega and limited. Eventually, we obtain Laplace equation. So this is Poisson. So Laplace is for ρ equal to 0. Great. So then we were able to find the energy, the electrostatic energy UE associated with a single point like charge in space. In this case, UE is equal to the work of the external forces to move a particle, and this is equal to using a reference that is normal conditions at infinite. This is nothing but the particle which we are attempting to move in space in the field generated by a particle 1. So Q2 is the particle we move in the field that is potential generated by particle 1, V1, at the point where the particle Q2 is located. Okay, so in other words, if we start from infinite distance and we bring our particle Q2 along any path we want, state function, to a point capital Q2, and here we have a point capital Q1 associated with the charge Q1, this generates a field. This is the distance R1, 2, between 1 and 2, okay? This is the electrostatic energy, which written using Coulomb's law gives us Q2 times 1 over 4 pi epsilon naught Q1 divided by R12. Okay, great. Okay. Then, the next thing we were able to do, it was to generalize this concept to the case of an infinite set, a large set, if you want, of point-like particles in space. So in this case, for a discrete charge distribution, U of E is given by 1/2, and we discussed a lot, we delved a lot into this discussion about this 1/2 sum for index I, which goes from 1 to the last particle, capital N, of Qi, the charge of the ith particle, times Vi, where Vi, I remind you, is given by the sum on another index J, which goes from 1 to capital N, with J different than I, of Coulombian type potential, 1 over 4 pi epsilon naught, Qj divided by Rij. Okay, great. So now, remember that to find this concept here, we define the concept of an infinitely far boundary. Behind this boundary, two particles do not interact with each other, so there is not interaction between any pair of particles behind this boundary, and these particles do not interact with the lab space here. So we took many of these particles, we brought them one by one into the lab, following whatever path we wanted, and by doing so, we were able to find this expression. Then we have done the opposite kind of concept So what we did next, we consider our boundary, our infinite boundary. We took an object, capital omega, we split it in an infinite set of infinitesimal cubes. For example, this one is a point capital Q. We split them and we spread them all the way outside this boundary. Okay, so now we have an infinite set of non-interacting particles infinitely far away, and then one by one we brought them back in to recreate capital omega, following a similar discussion as here. We were able to find the UE in this case by means of a mapping. 1/2 remains there. The sum becomes the volume integral in region omega, here, where the charge is defined with density rho. So we have density rho in this region of space, okay? And obviously, the charge becomes dq, and dq is nothing but rho q dv, which is drq cube. Okay, this is my charge dq, which is qi, and the potential v at point capital Q. Okay, total general expression here. Now, it so happens that if, in addition to this, we also have the rho is continuous and limited in omega, same condition as case 1 for Maxwell's equation for the electrostatic field. Under these conditions, then, and only under these conditions, we can write UE, forgetting about rho, as 1/2 epsilon naught, the volume integral in the entire universe, in this case, because we need to capture the whole field everywhere, omega capital omega infinite, absolute value of E squared, drq cube. All right. We also introduced the concept of delta Dirac, which allows us to Dirac delta. This concept allows us to, for example, define a rho for a point-like particle, Q. So in this case, for Q, it follows that rho at any point r vector is equal to Q delta of r. And we use this concept to show that for a point-like particle, you cannot use this expression because we are not fulfilling this condition. Instead, we need to use this expression, which gives us an energy equal to 0. And we also explore the case of a shell of charge, where we use both this expression and this expression for surfaces, however, in this case, because the charge was only on a surface, and we demonstrated that we got the same result. That's it.